All right, any questions come up on the homework so far, or have the practice quiz coming up at the end here today, so. You generated, yeah.
I had one. So on the coterminal angles, on the ones that are less than 360, it made sense because it would just be like the sum of 360 pretty much. But the ones that were greater than 360, there was one in the homework where it said the answer, so the question was 44 pi over 9. And it said the answer was 8 pi over 9. But I was thinking it was negative 10 pi over 9. So,
Okay. We have this problem. Find the coterminal angle theta to 44 pi over 9 with a theta between 0 and 2 pi for rotation. For this kind of problem, let's make sure this is coming out on the board here real quick. I have to zoom just a bit. Probably making you online busy here, huh? Okay, that works all right. What you do is you just keep subtracting multiples of 2 pi, but sometimes it's pretty tricky fractions is trouble. So you take 44 pi over 9 and say, how many multiples of 2 pi can I go in there? 2 pi would be 9 times 2 pi over 9. I'm multiplying top and bottom. I'm sorry. Yeah. Right, so multiplying top and bottom by 9, and this would be 18 pi over 9. So I think how many times can 18 pi over 9 go into this? It can go in twice, right? I could get 36 pi over 9 if I took twice that. 4 pi would be twice that, or 36 pi over 9. So what I'll do is I'll write this as 36 pi plus 8 pi over 9. Going with this here, this one is 4 pi. I can pull out 2 whole rotations there. So I'll say this is 36 pi over 9 plus 8 pi over 9. And then this one I replace with 4 pi. And say the coterminal angle, this is between 0 and 18 pi over 9, so it's between 0 and 2 pi. Our coterminal angle is theta equals 8 pi over 9. What's left when I subtract out a multiple of 2 pi?
So, but doesn't that go in the same direction though? As that
Yeah, it's okay to go in the same direction. In fact, you just want it to be between 0 and 2 pi, so you want it to be counterclockwise somewhere in here. Any others? I believe a week from Thursday, so 9 days from now, we have our first exam. So make sure you're getting caught up here. We'll go through at least everything I finished this week, probably through what I do on Thursday this week. So on Tuesday, we'll have a lot of review, and you can see if you want to bring more questions on that. Today, we want to remind ourselves that we have lots of identities and extend them just a little bit more to solve some more problems. Hopefully, we'll get going on triangles, actually. So just remind you that identities included. What did we have? We had sine squared plus cosine squared equals 1. This is the Pythagorean identity, and the proof is kind of neat, I think. If you can sort of remember it, if you remember that for any angle theta, let's put it in the first quadrant just so it's easier to look at. So it works in any quadrant. It's probably off the screen, is it? There we go. For any angle theta, I can drop a perpendicular to the x-axis. The coordinates of the point are cosine theta and sine theta. And so we said, if this side is cosine theta, and this side is sine theta, or in other quadrants it's plus or minus, and this side is 1, since it's a unit circle, that says cosine squared plus sine squared, or sine squared plus cosine squared equals 1 by the Pythagorean theorem. Therefore, that's called the Pythagorean identity. So that's the proof of it. Then if you divide this through by sine squared, or cosine squared, let's do first. Where cosine squared theta, remember, means cosine of theta quantity squared. This becomes sine squared over cosine squared plus cosine squared over cosine squared equals 1 over cosine squared. This one can be written as sine over cosine quantity squared. This one is evidently 1, and this is 1 over cosine squared. So, and recall the quotient identity also that we had. That sine over cosine is tangent theta. So this is tangent theta squared plus 1 equals secant theta. Was the reciprocal identity. Squared, we wind up with the other notation, tangent squared plus 1 equals secant squared. This notation meaning take tangent of theta and then square it. This was the second Pythagorean identity. And again, if you divided this through by sine squared, then you can instead get 1 plus cotangent squared equals cosecant squared. So those were the 3 Pythagorean identities. 1, 2, 3. These are harder to remember because they're not used as much. But I just wanted to point out you can figure them out. Divide through by cosine squared to get this one. Divide through by sine squared to get this one similarly. You want to make sure you know all of those. I'm going to make sure I keep up on attendance. What's your name? Just came in.
What? Jake Snyder.
Okay, thank you. Now we also had, in fact, we used it in there, the quotient identities. That tangent theta being, recall, y over x, and y was sine and x was cosine, you could write it as sine theta over cosine theta. I'm trying to show you some of the proofs of this briefly, makes them easier to remember, right? Remember that tangent is y over x, oh, it's just sine over cosine. Cotangent theta being x over y, this is cosine over sine. Those were the quotient identities. And then you have the reciprocal identity. So let's call this one 4, and we'll call this one 5. And we just did this part of them. And then the reciprocal identities that cotangent was 1 over tangent, secant was 1 over cosine, and cosecant was 1 over sine. And then there's the reciprocal of these. We can say also tangent is 1 over cotangent, cosine is 1 over secant, sine is 1 over cosecant because they're reciprocals of each other. I'll just leave it like that for now. I'll put this thing. Okay, now we can do some interesting things with these. What happens a lot in industry is you'll get an answer at the end of a problem, and it'll be a complicated trigonometric expression that actually represents something simple. This is out of the, let's see. this, okay. So suppose I wanted to solve a problem in industry and I came up with this answer, cosecant theta times tangent theta. How can I simplify that? Here's what you do. This is a big hit in simplifying. And so I'm going to put a bunch of classical problems up here that are on the problem set, but you kind of have to organize your mind to say, if I see this, I can do this. I see that, I can do that. It's kind of like a cookbook. You know, they tell you on those Master Chef programs or something, make a quiche or something. You got to know the ingredients of what to do, but they organize those things like that there, and similarly, we organize them here. When you see a simplification, a big hint, if you don't see something obvious, is to write the expression in terms of sine and cosine only. So that's a big hint. You can always do that because of these identities. That's why we wrote them all out. We'll say cosecant theta tangent theta. Cosecant is 1 over sine by the reciprocal identity. Tangent theta is sine over cosine by the quotient identity. We'll say this is equal to this by, let's see, 8 and 4. All right? And now the signs cancel each other. You have 1 over cosine, but 1 over cosine by 7 is secant. So there's the simplification. And what we're going to do shortly is graphs. This thing is really hard to figure out what the graph looks like, right? If that's the end answer in your engineering class or something. But this one, we're going to know exactly what it looks like, right? We're going to memorize all these graphs. Move this across the room. Okay, now, how about this one? Suppose I said simplify 1 minus cosecant squared theta. How about that one? This one you can write it in terms of sine and cosine, but it actually isn't going to help you that much. Instead, we want to go to the Pythagorean identity. I will write it in terms of sine and cosine only because that's an additional comment. The easiest thing to do is say, wait a minute, I remember seeing a 1 and a cosecant squared somewhere. Maybe I can do something with this. Well, cosecant squared is 1 plus cotangent squared. So this is equal to 1 minus 1 plus cotangent squared. Make sure you put this in parentheses so you subtract the whole thing, right? This is by equation 3, the third Pythagorean identity. All 3 of these are called Pythagorean identities since they all derive from this triangle. Now the ones cancel, and all this adds up to minus the cotangent squared. Now sometimes, to be quite honest, these identities, these last two and 3, are hard to recognize. What can you do? If stuck, go back to the strategy they're writing in terms of sine and cosine only, using the other identities. Right? And in this case, we'll say 1 minus cosecant squared. Cosecant is 1 over sine, so this is 1 minus 1 over sine squared. Right? Cosecant is 1 over sine. Cosecant squared is 1 over sine squared, and 1 squared over sine squared. Now what can I do with that? If you do it this way, you have to do a little algebra, but I say when you turn it to sines and cosines, often the identities are easier to recognize. So I'll put this over a common denominator. And let's see, now I subtract the numerators. Sine squared minus 1 over sine squared. What can I do with that? This one you'll start to recognize more easily soon. Sometimes this one is hard to recognize that looks like a Pythagorean identity, but almost everybody remembers sine squared plus cosine squared equals 1. You'll use that one a lot. So I recall my equation 1, that sine squared plus cosine squared equals 1. If I subtract sine squared from each side, let's subtract 1 from each side. Subtract 1 from each side and cosine squared from each side, and you get sine squared minus 1 equals minus cosine squared. By subtraction of cosine squared from each side and 1 from each side. Makes me realize the top I can replace with minus cosine squared. And now maybe you see it. This is a longer way to do it, but it's still 100% of the test. On the test, it has to be correct. It doesn't have to be the shortest. And what will happen sometimes is these equations 2 and 3, the harder Pythagorean identities, you don't recognize. But if you put it in terms of sines and cosine, what you do is when you do this for a while, when you see 1 minus sine squared, you recognize immediately by the first Pythagorean identity that that's cosine squared, right? Because you can add sine squared over here, and it would be sine squared plus cosine squared equals 1. Right? So from this identity, subtract sine squared, you get this. When you start to see 1 minus sine squared or 1 minus cosine squared, well, if you subtract cosine squared from here, then you get this. Always recognize you can rewrite that in terms of the other function. You see 1 minus cosine squared, you write immediately sine squared. You see 1 minus sine squared, you write cosine squared immediately. And this one is just that backwards, so it's minus cosine squared. Anyway, this is something that's going to come up all semester, is you'll see 1 minus 1 of these squared and need to reduce it. So this is longer for sure, and now cosine squared over sine squared, remember cosine over sine is cotangent, so this is minus cotangent squared this way. You can get the same answer with more work by just putting it in terms of sine and cosine, but often the identities are easier to recognize that way is the point. Right? So sometimes there's a short way and sometimes there's a long way. There's some problems like all of these on there. All right, so that's our identity so far. We have quotient identities, we have reciprocal identities, 3 more just like this, and we have the Pythagorean identities. What else can we do besides that? There's also some even and odd identities. And the even odd identity can be proved with the unit circle also. This is worth doing a proof because it's really short. And again, it helps you remember. If you just memorize, it's so hard to use this stuff afterwards because you're never quite sure it's right, you know. So what you do is you figure these things out from each other. And consider an angle like this. This works in any quadrant, but it's best illustrated in the first quadrant. Let's call this theta. And I'll drop the perpendicular. What are the coordinates of the point up here? The angle theta goes up to the unit circle. The intersection coordinates are cosine theta, sine theta. That's the way they're defined. Right? What if I take minus that angle and go the other direction the same amount? Then the coordinates will be cosine of minus theta, because I just turned minus the angle, sine of minus theta. And when I drop the perpendicular, where does it land? Same point, right? Because I turned the same angle but negative. So it drops to the same point. Now I notice if they drop to the same point, the x coordinates are equal. So cosine theta is equal to cosine of minus theta. So I'll say this implies that cosine theta cosine minus theta is cosine of plus theta. We just proved it on the unit circle, right? What about sine? Sine of theta is a positive y-coordinate. Since I turned the same angle but negative here, this length is the same as this one. And sine of minus theta, however, is a negative y-coordinate. I observe that sine of minus theta is the negative of sine of plus theta. Is the down instead of up. Those should look like something you've seen before. This is a definition that says sine theta is an odd function. And this is definite by definition says that cosine is an even function. At this point, you sort of have to remember your definitions from algebra. Let me write them down here. Anybody remember what an even and odd function is from algebra? One of the troubles in algebra is they introduce all the stuff you're going to use later, and you say, what do I use this for? And you don't remember it because you don't use it right away. If we're going to use it all here. Even and odd is for functions. And you say this, if f of minus x is equal to f of x, the minus goes away, then f of x is said to be even. And what graphing property does it have? Well, take any even function like y equals x squared is an even function. Any even power of x turns out to be even. And whenever you have a point x here, y is x squared, and when you have minus x, you get the same y coordinate. That's what it says. If you take f of minus x, you get the same y coordinates as put f of plus x. So this is x squared and minus x squared are equal. And what happens is every point here has a sister point over here. You can flip the graph over the y-axis and it lands on itself. Every point is symmetric across the y-axis, we say. That's the graph, the characteristic of the graph of the function that has this property. So this is the definition of even. Now odd is this, f of minus x equals minus f of x. If the minus comes out, then f of x is said to be odd. So these are definitions. And this one has a whole different graphical property. So you'll see if you take any odd power of x as an odd function, like take y equals x cubed, something like that, is an odd function. If you take any x here, you get the corresponding f of x. Because f of minus x gives you minus the y coordinate you got with plus x. And if you go over the same distance here to minus x, the y coordinate is just negative, the negative of this one. So this is minus x, f of minus x is minus this y coordinate. And so this time, every point corresponds to a point the same distance the other side of the origin straight across. We say odd functions have symmetry to the origin. Every point corresponds to another point over there. You can flip it over and then down and land on itself. So there's even and odd functions. This is the definition. This is what the effect it has on the graph. This one's symmetric by flipping over the y-axis. This one's symmetric by flipping each point through the origin. Does that look familiar? Okay. So what's going to happen is we're going to graph these soon, and we're going to find out these have the same properties. It turns out that every trig function, all 6 trig functions, are either even or odd. And so one of the reasons you did this in algebra was so that you could apply it in trigonometry. We'll apply this to the graphs later, but for now, let's just figure out which ones are even or odd and use them for solving a few identities in here. We know these from the unit circle, right? We could call these 9 and 10 or something. How about tangent of minus theta? What should that be? Again, I'm going to construct a proof here. And we are eventually going to have some proofs, although we want to keep them fairly simple, most of them. And the purpose here is so that you can remember this more easily. If I forget, it turns out tangent is odd. If I forget that, how can I prove it? Use your quotient identity, number 4 there, and say the tangent of any angle is the sine of that angle divided by the cosine of that angle, right? But if I know sine is odd, the minus comes out. Cosine is even, the minus goes away. And I pull the minus out of the sine to drop the minus on the cosine. Oh, minus sine over cosine is minus tangent. So tangent is even or odd? Yeah, it's odd because the minus came out. So there's that one. We can call that 11. We don't need the intermediate steps anymore. That's just the proof. I have to get rid of this to have enough room here. How about cotangent? Cotangent of minus theta. Similarly, I'll write that as cosine over sine. Remember, because of the reciprocal and quotient identities, every trig function can be written in terms of sine and cosine only. And that helps you to solve a lot of these identities, right? And we're going to use it for the even and odd properties here to solve these. So this is cosine of minus theta over sine of minus theta. Cosine the minus goes away. Sine the minus comes out. Cosine is even and sine is odd. Oh, that's minus cosine over sine is minus cotangent. These all look so easy when you see the identities up there. Try these though at home when you're not looking right at them. I'm going to put the shortly here list of the identities we've done now and the ones that are coming up on D2L under the files out there. So look under files, you'll find the syllabus there and the book and the UCO supplement. And in that same place, we'll find the identities page that I'll put out there. All right, finally, secant of minus theta is 1 over cosine of minus theta. Cosine the minus goes away. Oh, this is 1 over cosine is secant. Proves that this is actually even. So cotangent was odd. I should have written that down there. This one's even. And then finally, cosecant of minus theta being 1 over sine of minus theta. So minus comes out of sine. And we have minus cosecant. So there's the proof of that one. Cosecant is odd. Oddly enough, let me say that, 4 of these are odd and 2 of them are even. You'd think, oh, maybe they come out half even and half odd. They don't. This gets hard to remember. The way I remember this is cosine. These are easy to remember, right? Sine is odd and cosine is even. Cosine and its reciprocal secant are even functions. All the rest are odd. So cosine and its reciprocal are even. You can see why this reciprocal is even because cosine is even. So that's the way I remember it. You can remember it however you want. You have to be able to repeat that on the exam. It will be open book tests. You can keep the cheat sheet of all these things when you take your tests. However, I will tell you that they're timed tests. So if you have to look up all this stuff, you'll have a real hard time finishing. There is our list of identities now. How about that? Quite a lot of them. Any questions on all those that you want to look at? Carry this over here then. We can fit this in. Now, some very important things you want to be able to solve. I said one thing you want to be able to do is reduce identities by writing them in terms of sine and cosine only, or by applying one of these identities directly. Another thing you want to be able to do is this. We mentioned this last time. I want to repeat it because we're going to deal with the newer trig function. Given any trig function value and a quadrant for the angle, all fixed trig functions are known. And here's what you can do in that. Here's an example. Suppose cotangent of theta is minus 4/3, right? And suppose theta is between pi over 2 and pi. Find all the other trig functions. Right? How can I do that? This is a good kind of problem I might put on the exam. One of the concepts I want you to know is given one trig function of quadrant, you find all of them. Actually, you need even less than that. I can give you one trig function and the sign of an unrelated trig function, plus or minus. And that will tell it to you all by itself, actually. How about this? If I know cotangent, what else do I know? Yeah, I know tangent immediately. So 1 is the tangent theta is its reciprocal is immediately known. So I just turn this upside down, minus 3/4. By the reciprocal identity, I erased it. What else can I do? There's a number of ways to go, which you'll find is you might have a favorite way, and it might not be this one. You're welcome to go a different direction. Another identity I know is that cotangent is related to cosecant. I know that 1 plus cotangent squared equals cosecant squared. Right? So I can solve for cosecant squared by square rooting. And I'll say cosecant theta is square root 1 plus cotangent squared. But what did I get wrong here? This one. I say x squared equals 4. What's x? Plus or minus the square root of 4, right? This notation means the non-negative number whose square is 4. It means 2. So there's 2 answers. And same thing here. If cosecant squared is this number, cosecant can be either plus or minus the square root of the other side, right? So I'll put that in. And now cotangent squared was minus 4/3. So this is plus or minus. Oh, and then do I put plus or minus? This is where the quadrant comes in. If theta is between pi over 2 and pi, you have to remember your angles now. Pi over 2 is a right angle. Pi is a straight angle. That puts me in quadrant 2, right? In quadrant 2, actually, I should put, I can put this. It's not on the quadrant because cotangent minus wouldn't be this number. So it's in quadrant 2, and in quadrant 2, cosecant is what? I've got some angle out here. Cosecant positive or negative? Yeah, you have to figure it out, but in every quadrant, each one of the trig functions has a consistent sign. It's either positive in the whole quadrant or negative in the whole quadrant. What you can do is say, in this quadrant, x is negative, and y is positive, right? That's what these coordinates are. All the points where the x coordinate went left, the y coordinate went up, so x is negative, y is positive. Now cosecant, right, is 1 over the sign, or 1 over y. So it's 1 over a positive number. In this case, I want to choose the positive. So I would have got lucky if I forgot my minus mistake. If I was looking for secant, it would have actually been negative. So you look in the quadrant and say cosecant is either you say it's 1 over y or it's 1 over sine in this quadrant. And so it's y being positive, cosecant is positive. So I'll put plus, and now I'll say this is square root of 1 plus cotangent squared is minus 4/3 squared. It's square root of 1 plus, and you square this. 4 minus 4 squared is plus 16. 3 squared is 9, and so you get 16/9. So what do I do with the 1? I can write 1, but Yeah, you want to reduce this, you have to put it with a common denominator. So I'll rewrite 1 is 9/9, so I can add these. So this will be algebra intensive. You'll be better at your algebra when you come out, which is good because a lot of the reason people have trouble in calculus is their algebra is bad. This will perk up your algebra skills just a little bit. All right, so cosecant theta, I can get rid of this now. Is square root of, you add fractions by numerator plus numerator over the common denominator. So this is 9 plus 16/9 is 25/9. Those are both squares. We get 5/3 here. So cosecant theta is evidently 5/3. What else can I do now? Yeah, so cosecant, sine is reciprocal of cosecant. I just turn that one upside down, right? Use an identity. And I say it's 3/5 instead of 5/3. Finally, I need cosine and secant. How can I get those? There's multiple ways to do this also. So there's a number of ways. You could say, go back to the beginning, say cotangent is -4/3. That was given. But cotangent is also cosine over sine. And sine is 3/5. This is one way to do it. So I can multiply both sides by 3/5 and get cosine theta equals -4/5 times 3/5, right? If I multiply both sides by 3/5, that cancels this denominator here and multiplies 3/5 over here. And now, oops. This is -4/3, I miswrote it. Now the 3's cancel, and I get -4/5. There's cosine. Once I have cosine, I know immediately secant. This would be the last one, 5. And secant theta is the reciprocal of cosine is -5/4. There it is, all 5 other trig functions. And there are other orders to do this if you prefer. Like once I have sine, one important thing to know is I immediately know cosine. Engineers often do this. You know, sine is right, cosine is plus or minus square root 1 minus sine squared by the Pythagorean. I solve for cosine. So that's a good way to do it too. Questions on all that? You can do this with different identities in different orders. But recognize that once you know one trig function and either a quadrant or just the sign of the unrelated trig function in the quadrant, then you can find all 6 trig functions. Here's another kind of problem that's very important. If I know sine and cosine, I know all 6 trig functions. This is a common problem I give too. So if you know, say, the values of 2 trig functions, such as sine and cosine, given sine theta and cosine theta, by the identities, all 6 trig functions are known. So this is another thing you can do. Oh, I wanted to point out something on this last example too. If you look at this carefully, if you look at this thing carefully, all of these trig functions we came out with are quotients of the same numbers, 4, 3, and 5. This is plus or minus. This is 4/3 minus, this is 3/4 minus. This one is 5/3, right? Everything has 3, 4, and 5. It all comes out of that 3, 4, 5 right triangle with pluses and minuses. But you'll find this characteristic when you, there won't necessarily be whole numbers here. A lot of times there'll be square roots. But you'll find out that on these problems where you have to find the 6 trig functions, they're all just ratios of the same 3 numbers once you simplify. So 3, 4, and 5 in this case, harder numbers than most other cases. This is the simplest numbers we can get, really. But look for that when you're solving these, you know, there's -4/5, -5/4, so forth. Those three numbers come up over and over, and the same thing will happen here. Whenever you get all six trig functions, it's just plus or minus ratios of the same three numbers. So given sine and cosine, all six trig functions are known, so suppose I have this example. Suppose sine theta is 7/24, and cosine theta, actually, let's just do, I want to do it more like a homework problem. And theta is in quadrant 2, find all six trig functions. This goes back to the last problem. Given one trig function and a quadrant, find all six trig functions. But this is going to illustrate this concept here. This is an important identity, this Pythagorean identity. We can immediately, once we have sine, write cosine is plus or minus square root 1 minus sine squared. I often start it like this. If I'm given either sine or cosine, I immediately write the other one like that. How do I know that? Yeah, the Pythagorean identity. It's from sine squared plus cosine squared equals 1. If I subtract sine squared, then I have cosine, I'll say this implies cosine squared equals 1 minus sine squared. And then I square root it. If cosine squared is that number, then cosine must be plus or minus the square root of that number. That's what it is. It's the Pythagorean identity solved for cosine. This is extremely common in use.
Use the Pythagorean one for root 4 on the last problem.
Yeah, you can do that. That's what I'm saying. There's different, you can do these in different orders, and the Pythagorean identity is often the way people like to go. Okay. So on a lot of these problems where you're given a trig function and quadrant, the thing to do is use a Pythagorean identity to start. And I'll say, is that plus or minus? You go to quadrant 2. In quadrant 2, if you have an angle here, and you drop a perpendicular, think of the unit circle. X is negative and y is positive. So cosine is negative and sine is positive. So cosine must be negative this time because I'm in quadrant 2. So I'll put the minus, and now I know cosine is minus square root 1 minus, sine is 7/24. And I need to square that. Now these are getting to be harder numbers, right? So this is where you need your calculator in the exam. Every exam you need a calculator because you'll have computations like this that what is 24 squared? You'll lose a lot of time trying to do that if you don't have your calculator. 7 squared is 49. 24 squared, I'm going to figure it out here. My calculator brought it. I sort of figured it out, but it'd be better to do it this way. 576. And then 1 is 576 over 576. Minus. Evidently the cosine, if you subtract this, 527, is that what we got? Let's see. 526. Minus the square root of 527 over 576.
something wrong here. Just got an old.
So in this calculator, it just leaves it like that, it doesn't reduce. So I'll leave this as minus the square root of 527. But I remember the 576 is the square of 24, so it's over 24. And a lot of times your answer will just come out that nasty. But you can still finish the problem. It just comes out to be those three numbers that you see there, 7, 24, and square root of 576. Right? How do I now find, having sine and cosine, I said now you can know all 6 trig functions. You just say tangent theta by the reciprocal is, or the quotient identity is sine over cosine, right? Sine was 7/24, and cosine was minus square root 576 over 24. The 24s cancel, but you have to be careful on these. I'm going to recommend in general that what you do is, here's the trick. If you take 3/4 over 5/4, what's this quotient? The 4's cancel and you have 3/5. But what if I have 3/4 over 4/5? You might be tempted to cancel the 4's, right? They don't cancel. The rule is you take top times bottom over middle times middle is 3 times 5 over 4 times 4. So be careful canceling. You can cancel both denominators and do this in the long run because you want to be quick. You cancel the same numbers if they're in both denominators or if they're both numerators. If you have 3/5 over 3/4, you can cancel the numerators and write this as 4/5. Just to be careful, if you're not sure what you're doing, what you do is you write top times bottom over middle times middle. So you write 7 times 24 over square root 576 times 24. Now the 24's cancel, and you've got 7 over square root 576. This is a good answer for me, and I like this better than the next one, but if you're going to rationalize the denominator for comparison purposes, then you ought to write it, this is what will be in the answer key. 5 square root 576 over 576. Is there a question? Yeah.
Why is it 576 over 24 instead of 527 over 24?
Oh, I'm sorry. Yeah, because I mistranscribed. Yeah. I have this my mistake. Yeah. 527. Thank you. And similarly here in that.
Yeah.
Thank you for catching me before I get too far along here. All those 576 and 527. All right. But now I've got my 3 numbers. I'm going to leave this one out because this is easier to write. Right? This is the officially algebraically simplified form, but that doesn't look simplified. This is easier to write. And here's the advantage of writing it this way. Even though to check the answer key in the back, you want to write it this way. Cotangent theta is now the reciprocal of this. You just turn it upside down, and it's already rationalized, right? Square root of 527 over 7. How about that? So now the idea here is once you have sine and cosine, you write 3 reciprocals. Secant now is 1 over cosine. You just turn the cosine upside down. Cosine was square root of 527 minus square root of 527 over 24. So secant is minus 24 over square root of 527. And cosecant being the reciprocal of sine, you just write the sine upside down, is 24 over 7. But notice every one of these ratios, once again, has either 24, 7, or square root of 527 in it. And you get all 6 ratios out of this, plus or minus. But that concept that once you know sine and cosine, you know all 6 trig functions, you know how useful that is. Those identities fall real naturally with reciprocals. And you can use that to solve these problems where you're given either sine or cosine and you're asked to find all 6 trig functions. Well, there's a few abstractions of this that you want to be able to do too. Given, this is another kind of problem that comes up a lot in all sorts of applications. Given a point on the terminal ring, of angle theta in standard position. All 6 trig functions can be known exactly. When we're given this will do it too. We'll be able to do this kind of problem. For instance, suppose I did this example. Suppose I said the point with coordinates minus 12 minus 5 is on terminal ray for angle theta. Evaluate the trig functions. All 6 of them. What am I going to do?
You have sine and cosine.
Yeah. Some people have mentioned to me they've seen the XYR diagram before. You can use that XYR diagram. I'll do it like this. If you have the point minus 5, 12, there's your terminal ray. You can drop a perpendicular like that, and consider the unit circle that has that same angle in it. Now, this point here has coordinates for angle theta. What are the coordinates of this one? Oh, it's cosine theta and sine theta, right? So what are the coordinates here? I can find the hypotenuse here, since this is a 5 by 12 sides here. The last side, by the Pythagorean theorem, is square root of 5 minus 5 squared. 12 squared is 13. So the hypotenuse of the triangle is 13. If the coordinates here are cosine theta and sine theta, what are the coordinates here? They're 13 times as far out because the radius here is 13. The coordinates here must be 13 cosine theta and 13 sine theta. So, I have from here that 13 sine theta is the y coordinate 12, and 13 cosine theta is the x coordinate minus 5. From which I can deduce sine and cosine. Sine theta must be now, oops, wrote this wrong. Yeah, no, that's right. I divide by 13 and get sine theta is 12 over 13. Divide by 13 here and get cosine theta is minus 5 over 13. Once I have those two, I have all 6, right? Now I say tangent theta is their quotient. 12 thirteenths over minus 5 thirteenths. This time I'll do it quickly. We'll say both these are denominators. I can cancel them, right? This is minus 12 fifths. Once I have the first 3 trig functions, I find the last three as their reciprocals, the easiest way. So cotangent theta, turn this one upside down as minus 5/12. Secant theta, I turn cosine upside down, make it minus 13/5. And sine cosecant theta, I turn this one down, upside down, and write 13/12. Once again, it's the same three numbers, 5, 12, and 13 this time. Just plus or minus and plus or minus ratios of those. Yeah.
The original coordinates were -12, -5.
Oh, I'm
So,
sorry, yeah, I
so
changed it.
is that gonna change anything major?
Yeah, it changes the whole thing. I should fix the problem. You're right, I was,
I just didn't know if it changed anything.
yeah, it
major.
changed everything, yeah, let's put it back. I messed that up. Thank you for catching that. Well, yeah, I'm just gonna change the coordinate. So let's say the point, minus 5/12 is on.
Okay.
So just change that minus here to a plus and everything works. Sorry about that. I was trying to put this one in quadrant 3 because I've been doing quadrant 2 and I switched it and forgot. Yeah. All right, so there's a lot of new techniques for evaluating these things. Yeah. There were a few simple problems like this. I just wanted to point out using some of the identities. Those are the main things we want to consider. Well, we haven't done as much with the even and odd identities as I wanted to do here today. Let's give you a couple of those. Whenever you have a sine or a cosine or a trig function minus an angle, you can use the even and odd identities to find the corresponding positive ones. Suppose I said if, this is number 16 of the UCO supplement. If cotangent, cosine of t or theta is 1/2, find cosine of minus theta. How about that? Whenever you know a sine or cosine of plus an angle, you can do the minus one also. What is it? This one's really easy. Yeah, remember the cosine is an even function, the minus goes away. So it's just 1/2 also. How about this one? This is the next one here. If tangent theta is minus 1/4, find tangent of minus theta. Tangent of minus theta is what? Yeah, and tangent of minus comes out, right? It's an odd function. So an even function, the minus goes away. An odd function, the minus comes out. Tangent theta is minus 1/4, so I have minus of minus 1/4 is plus 1/4, as was indicated. Perfect, yeah. So that's it. When I ask you to do a trig function of minus an angle, it's just plus or minus the corresponding trig function without the minus. And it depends on whether it's even or odd. All right, so try some of those.